Okay, so in this video we're gonna review what linear independence is, and then just kind of try to relate that to kind of formalize what linear independence and span and put those concepts together, right? Which we've kind of hinted at in previous work in our course here, but now we're gonna we're gonna more in depth here. All right, so just as a reminder, if you're given a set of vectors v1, v2, v3 to v sub n. All right, so given this set, all right, this set is, so we'll establish a relation of linear dependence. So that means we write it as a linear combination set equal to the zero vector. All right, now one thing to keep in mind is that this relation of linear dependence always has a solution, right? So it's a consistent system, right? Again, we have parallels to a homogeneous system, which we know is always consistent because the trivial solution always exists. All right, so that is not a question that is being asked whether solutions exist or not. We know that one exists. We know we have a trivial solution. Okay, that is C1, C2 equals to C sub n equals to 0. All right, so that always works. All right, so now we ask ourselves, is this the only solution, right? And again, also what we know about linear systems, right? Their options are no solution, one solution, or infinite solution. So here, if we know that there is at least a trivial solution, well, is there another solution, i.e. is there infinite number of solutions for this? Right now, if there is only the trivial solution, okay, so if this is the only one that works, then we have, then the the vectors are Li. Linearly independent. Okay. All right, if a non-trivial solution exists, then the vectors are linearly dependent. Okay? All right, so let's take a look here at a theorem here from our textbook. All right, so we're looking here at theorem DLDS. Now it says, suppose that S is a set with n vectors, then S is a linearly dependent set if and only if there is an index T such that UT is a linear combination of the vectors U1 through UT minus 1, UT plus 1, UN. Okay, now a couple things to kind of decipher here. Now the first thing is we see the statement if and only if, right? So that's telling me that we are dealing with an equivalence relation, right? And what that means is that this goes in both directions, right? So it's so much stronger than an implication. If this happens, then the result is this, right? What we have here is equivalence. So if I tell you it's linearly dependent, the other one automatically follows, right? I can write one of the vectors as a linear combination of the remaining vectors. If I can write the linear combination of one of the vectors in the set with the remaining vectors, then that is linearly dependence. Right, essentially a equivalence or a definition of sorts here for linear dependence. Okay, all right, so for example, all right, and again, dependent meaning, right, you can think of it as the vectors depend, a vector depends on the other vectors in the set. All right, so let's take a look here at an example. So let's say we had the vector set 1, 2, 3. 2, 4, 6. And then 1, 0, 1. So let's start by kind of setting up a coefficient matrix, right? So here, if I call this my, so if I call this V1, V2, V3, all right, then let's say alpha 1, V1 plus alpha 2, V2 plus alpha 3, V3 is equal to the 0 vector. Okay, so we get alpha 1 times 1, 2, 3 plus alpha 2, 2, 4, 6 plus alpha 3, 1, 0, 1 equals to the 0 vector. All right. So now we can write that as 1, 2, 3 as a homogeneous system, right? It's 2, 4, 6, 1, 0, 1, where the columns are V1, V2, V3. Okay, all right. And I don't bother augmenting it with the 0 vector, right? We just kind of implicitly have it there. So I perform my reduced row echelon, and then I get the matrix 1, 1, 2, 0, 0, 0, 1. Okay, now again, how do I interpret this here, right? So we have 2 pivots. Okay. So that means that I have 1 free variable, right? Now in terms of what this last row tells me here is that alpha 3 is equal to 0. Right, remember, we don't write that last column of 0 vectors. So alpha 3 is equal to 0, and then alpha 2, that's my free variable since there's no pivot there, so I'll just call that t. And then alpha 1 is equal to negative 2t, right? So that's how I would interpret that, right? Now, so what that means is setting t equal to 1, right, going back to our linear relation here. So this means that negative 2 times v1 okay, so that equals to the 0 vector. Okay, now more importantly here is that I have a non-trivial solution, right? So that means that, again, when not all of these are 0, now notice one of them is 0, but that's okay, right? As long as I have one where not all of them are zeros, then I am okay, right? I'm here okay in the sense that this set is linearly independent, right? And then just kind of rearranging the terms here, the way you can think of this is if you bring this essentially over to the other side, we have 2, 4, 6 is equal to 2, 1, 2, 3. Right? Or in other words, V2 is equal to twice V1, right? And again, going back to our theorem, that is the equivalence relation that we have, right? So here we see that UT, one of the vectors is a linear combination. In this case, it's just a multiple of one of the vectors, right? But that's also still a linear combination, okay? All right, so the idea here all right. Okay, now if a vector is redundant, right? So here's what we kind of are showing here when you can write it as a linear combination of the vectors. That means that in terms of right the span, I don't really need it to be in my base set. Okay, so if I remove it, right? So the next step here is to think about here is if I have the set V1, V2, V3, right? And I saw that V2 is just double V1, so let me just remove V2, right? So if we have these two sets of vectors, which are clearly different, right? One has 3 vectors, the other one has 2, right? How does that affect the span? Right, this is our next question that we set out to ask. How is the span affected by removing any linearly dependent vectors?